Hello everybody, this is week 10, lecture 1, and lecture 1 is all one part this time, and today we're going to start a new topic called hypothesis testing. We'll see that this is actually quite closely related to confidence intervals in that a lot of the same rules apply. So there'll be a common form for a hypothesis test, and so it's largely fill in the blanks again in this particular part of the course. And this is the second last topic in the course. Hypothesis testing will be followed by linear regression, which is the last part of this course. Okay, so hypothesis tests are basically statistical tests on two competing hypotheses. As mentioned, it's closely related to confidence intervals, but this is what I call a formal test. So if I ask you to do a test, I want to see a hypothesis test. I don't want to see this done using a confidence interval because there are some differences, and I'll try to explain where those differences are as we go along. Particularly in hypothesis testing, a lot of our tests are actually one-sided, whereas confidence intervals are often two-sided. There are also a couple of significant differences between confidence intervals on proportions and hypothesis tests on proportions, and again I'll try to explain where that comes about. That'll probably be next week in week 11. Okay, so before doing anything else, we have to define what we mean by these hypotheses, and basically there are two competing hypotheses that we're always going to be dealing with. H0 we'll call the null hypothesis, and this is the default condition or the default claim. One of the things that you have to remember is that the null hypothesis can never be accepted nor proved. The test doesn't prove the null. It can only prove the alternative. So if we fail to reject the null hypothesis, it doesn't mean it's true. It means it could be true, but we haven't proven that it's true, so we can never accept it. In other words, you should never put into the null the thing that you're trying to prove. Okay, that's where we put the thing we're trying to prove. We put into HA, which is the alternative, and this is the one that can be proved. Basically, we go out and collect data, and if our data are far enough away from the null hypothesis in the direction of the alternative, then we reject the null and conclude that the alternative is correct to some level of confidence, 1 minus alpha. So just make sure that whatever you're trying to prove, you put into HA. The other thing that I'll try to keep mentioning is that the null will always include the equality. So there's going to be three types of tests. There's two one-sided ones. There's a less than or equal to. There's a greater than or equal to. And then there's an equality one where we've just got equal to. But in any case, the equal sign always occurs in H0, never in HA. Okay, some examples, really classic examples of hypothesis tests we live with all the time. One is our entire judicial system is based on a hypothesis test. The idea, innocent until proven guilty, is our null hypothesis. The null hypothesis, by default, you're assumed to be innocent. You are only proven guilty when enough data is collected that that is far enough away from innocence in the direction of guilt to prove that you are guilty. And this will be done at some level of confidence. We're never going to be 100% sure that you're actually guilty, and so sometimes we make mistakes in the judicial system, and that's unfortunate, but there's really no better way of doing this. By the way, if we are unable to reject H0 and prove guilt, it doesn't mean that we've proven innocence. You could still be guilty, just not found out. So we do not prove innocence. We just, if we fail to reject H0, you could be innocent, but we haven't proven it. The entire scientific method is also a hypothesis test. The basic idea is that we set the null hypothesis to be our current theory, and our new improved theory is our alternative. We go out and collect data, and if there's enough evidence to show that the new improved theory is better than the current theory, then we reject the current theory and adopt the new theory. So that's the whole way scientific method proceeds. We just keep building on old theories with new theories and we keep the ones that are better. So an example, Always Ready Battery Company claims that their batteries last for at least 10 hours under continuous use in a certain flashlight. You are doubtful, decide to carry out a test. What hypotheses are appropriate? Well, if you're doubtful about the claim, you want to put into HA what it is you're trying to prove. And if you're doubtful, then you're trying to prove that the mean battery life is less than 10. By the way, it doesn't say anything about mean here, but this will always be a test on means or proportions, because we would not do a test on an individual observation. A single battery is either greater than or less than 10 hours. We know as soon as we tested it. So basically we're asking here, is the mean less than 10 or greater than 10? So since HA can be proved, we would put mu x less than 10 into HA. So that's what I've done down here. That means the null hypothesis is mu x greater than or equal to 10. And like maybe I didn't mention, we're always going to use the equality here. So we're going to actually test mu x equal to 10 because that's the hardest of all these possibilities to reject. In other words, if the x bar is 8, that's saying that HA may be correct. It's as close as you can get to 10. But if we took mu x equal to 11, then it's easier to reject because H is farther away from 11. Okay, so yes, as I mentioned, this is what we actually test. Mu x equals 10. It's the hardest to disprove. And it also gives us a distribution to use. So this tells us what the mean is that we're going to use to judge our results. So if we're sufficiently far away from the mean in the direction of HA, then we reject the H naught and conclude that HA is correct. And as I mentioned, then the equality always has to be on H naught. Okay, so the basic idea behind a hypothesis test is we're going to collect some data and evaluate if the data are sufficiently far away from H naught, but it has to be in the direction of HA. Okay? If so, then we reject H naught and conclude that HA is correct at a certain level of confidence. I always perform my test by remembering the following sentence. We reject H naught if our test statistic, blah, 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 is something then something. And then it's just a matter of filling in the blanks. So I encourage you to remember this sentence. So in more detail, we reject H naught of our test statistic. And this test statistic will look something like this. Something is equal to something minus something over something. And we just have to fill in these blanks. The thing on the left-hand side is either going to be Z or T. And this follows the same rules as we had for confidence interval. Use T if it's a test, hypothesis test on mean or differences in means, where sigmas are unknown, and use Z for everything else. And this Z or T is really a standardized variable. And so what's going to happen in here is I've got the estimate of the whatever the test is on. So it's a test on mu x. This is x bar. And then subtract the mean according to the null. Okay, so this will be the mean that's specified by H naught that goes in here. And then underneath here is the standard deviation of whatever you put in here. So there's a couple of parts here that are exactly the same as we had for hypothesis testing. This is the estimate of whatever the test is on, and this is the standard deviation of that estimate. Okay. The rest of the sentence is this is going to be less than, greater than, or either less than and greater, or either less than or greater than, depending on what HA says. So this is in the direction of HA. And then the than here is the criterion. So this is the rejection criterion for the test. We'll see more examples of this as we go along. And then, as I said, all we have to do now is fill in the blanks, and then we can make a decision based on this test. As mentioned, test statistic follows exactly the same rules. Here are the bits and pieces, as I mentioned. Z or T on the left-hand side. Estimate of whatever you're doing the test on goes in here. The mean, according to H naught, goes in here. And the standard deviation of the estimate goes in here. And this is either going to be sigma or S of whatever this estimate is. The other interpretation of this is that Z or T then is the number of standard deviations that our estimate is. And in this case, I put X bar, but it could be X bar 1 minus X bar 2, or it could be P or P1 minus P2 with hats on them. It's the number of standard deviations that estimate is away from the claim according to H naught. And if this number of standard deviations is large in the direction of HA, then we can generally reject H naught and conclude that HA is true. Okay, so here's an example. Suppose we are testing H naught, the mean is greater than or equal to 10. And as I mentioned, we're actually going to test mu x equals to 10, because this is the hardest to reject, versus HA, mu x is less than 10. So this is a one-sided test, and I'm going to reject H naught if my test statistic, which is basically x bar standardized, is sufficiently far away from 10 in the direction of HA. So if I get an x bar that's 11, there's nothing I can do here. This is already in favor of H naught, so I can't reject H naught. But if I get an x bar that is 3, it suggests that's in the direction of HA. It suggests that this is wrong, and it's actually quite a long ways away from the claim of 10. But how far away depends on how variable this process is. If I get an x bar of 3, and it turns out the standard deviation of this process is 100, 3 may not be very unusual. Okay, so we may not be able to reject on the basis of seeing a 3. Okay, so let's suppose we have this. This is our test, and we've collected some data from 16 observations. So n is 16. Suppose x bar is 8.3. So that's a little bit less than the claim of 10. It's in the direction of HA, so we might be able to reject H naught. We'll have to see. And suppose our sample variance is 9. So our sample standard deviation is 3. Okay, x bar is 8.3, is less than 10, suggests that H naught may be false. But since mu is 10, then x bar is equally likely to be above or below 10. And so 8.3 may or may not be particularly surprising. So is it far enough away below 10 to suggest that mu x equals 10 is wrong? To decide, we compute the number of standard deviations that x bar is below the claimed mean. Below in this case because it's in the direction of HA, and the claimed mean is 10. Our test statistic gives us this distance. So we have our hypotheses are shown here, and our sentences as follows. We reject H naught if our test statistic, and we write down these brackets, something equals something minus something over something, and start filling in the blanks. In this particular case, I don't know the standard deviation, the true standard deviation. I know the sample standard deviation. So the left-hand side is going to be t. And on the right-hand side, the first one is the estimate of whatever we're doing the test on. The test here is on mu. So the estimate of mu is x bar. Minus, and in this one here, I put the claimed mean of x bar according to the null. And that's 10. So I put 10 in here. And underneath, I get the standard deviation of x bar, which we know is Sx over square root of n. Okay, and that's the sample standard deviation, because true standard deviation is unknown. I know everything now on the right-hand side. It's 8.3 minus 10 over 3 divided by root 16. I get minus 2.27, which basically is saying that x bar is 2.3 standard deviations below the claim of 10. And then I complete my sentence. The rest of the sentence is something then something. And the first something is the whatever you've got here. If this is a less than, you use the word less. If it's a greater than, you use the word greater. And if it says not equal, then it's either less than or greater than. Okay, so this is less than, so we're now looking in the negative direction. So if this test statistic is less than minus t alpha n minus 1, so the minus sign is in the negative direction. So basically, anytime you see less here, you should see a minus sign here. Okay, if it's greater than here, you should see a plus sign here. And then our rejection region is going to be t sub alpha with n minus 1 degrees of freedom. The n minus 1 comes from the fact that we've got, this is an x bar calculation with s squared. The number of degrees of freedom of this thing is n minus 1. And we're going to reject if we're anywhere beyond t alpha n minus 1 standard deviations below h naught. And then we choose our alpha. When we choose our alpha, we get a number for this quantity here. We check to see if minus 2.27 is less than that number, and if so, we reject h naught and conclude. If I got this conclusion coming in down here, yeah, I'll say it. We reject h naught and conclude with at least 1 minus alpha confidence that mu x is less than 10. Okay, so this is an example of that. Since HA mu x is less than 10, this is a one-sided test. So we're using alpha rather than alpha by 2. So that's where that alpha is coming from. Okay. If this had been not equal to, then we'd be testing if we're far enough away in either direction, in which case this would be alpha by 2 here, not alpha. Okay, so if you wanted to test this particular problem at alpha equals 0.05, so this is a 95% confidence level. So this gives us a 5% probability of rejecting H naught when it is true. Then my T alpha with n minus 1 degrees of freedom is T 0.05, 15 degrees of freedom. I looked this up in the T table. I get 1.753. And since our computed test statistic minus 2.27 is less than minus 1.753, we do reject H naught and conclude with at least 95% confidence that mu x is less than 10. Okay. So summary here, we've got our hypothesis H naught always has the equality. You can put the less than or greater than in here as well, as long as the equal sign appears here. And we use it. We do the test at the equality. The alternative has three possibilities. One could be a one-sided test with a less than here. It could be a two-sided test with a not equal, in which case we test to see if we're far enough away in either direction. Or it could be a one-sided test with greater than, in which case we check to see if we're far enough away in the positive direction. And we reject H naught if our test statistic, something equals something minus something over something, is one of these things away from HA, in the direction of HA, then some rejection critical value, which is going to be Z or T at some alpha or alpha by 2 probability. If we do reject H naught, then we can conclude with at least 1 minus alpha confidence that HA is correct. If we fail to reject H naught, again, I'll emphasize this, then we can only say that H naught may be true. We have not proven it to be true, and it cannot be accepted. The test does not prove H naught, it can only prove HA. And that's it for the intro to hypothesis testing. So I will stop there, and we'll resume with the second lecture in week 10, whenever you look at it. Thank you. Bye-bye.